Alright, good morning class. This will be a sample recorded problem solving that I'm gonna do to you so that you can better approach the assessment quiz that I gave you. So this problem set in here is slightly similar to what I gave you in your assessment, and I'm gonna teach you how we should approach solving this particular problem. So the problem asks us to solve for the main current I and VO in this last 35 ohm resistor network in this circuit diagram. So the first thing that we can do here is to solve for current I. So and we need to simplify the resistor network first so that we can solve for the main current. So when we simplify the resistor network, it is important that we start on those resistors which we can easily add onto each other. Say for instance, this resistor network right here and this one right here. So for the purpose of annotating the equivalent resistors, this resistor network right here, we shall call it equivalent resistor 1 or REQ1, and this one right here will be REQ2. Okay, so solving for REQ1, which is again this one, we have is equal to, we will use a parallel resistor method of adding. So we have R1 R2 over R1 plus R2. So 35 times 35 over 35 plus 35 REQ1 would then be 17.5 ohms. So REQ2, again this is REQ2, so that's a more simpler addition problem. So we just need to arithmetically add the two resistors, and we have REQ2 is equal to 70 ohms. Take note for this example so far that when we add resistors in series, they would just be equal to twice the value, and when we add resistors in parallel, say for instance this one, the equivalent resistor would be half of what the selected resistors used to. So once we get the two equivalent resistors, we can now further simplify the diagram, and let me just redraw it to you. Continuing on to this top page, we have this one, we have another resistor right here, and another resistor right above. Then we have here, now we have the equivalent resistor 1, which is this one, and REQ2 is right here. The rest will just follow the values for resistors. So what we can do next is that we can add this one because they are just in series, and we call this as our REQ3. Wait. So continuing on to the problem set, we have REQ3 is equal to, again, this is 35 plus REQ1. So we have the value for REQ1 right here, which is 17.5 ohms. So we're just gonna add that onto the 35, and then we have REQ3, which is equal to 52.5 ohms. So again, this is the value for REQ3. And what we can do next is that we can then add this resistor network here in order to simplify it. So we'll just do the undo, and we call that as our resistor network 4, or resistor equivalent 4, or REQ4. So REQ4 is simply a parallel sum of this resistor network right here. So we have 52.5 times REQ2, which is equal to 70 ohms. So we have 70 and 52.5 plus 70. So we have 52.5 plus 70 is equal to 122.5, and 52.5 times 70 is equal to 3,675. So that's a hefty amount. We divide that by 122.5, and we obtain resistor equivalent REQ4 is equal to 30 ohms. So we now have a value for this resistor network right here. So this resistor network right here is equal to REQ4, which is 30 ohms. Now, let us simplify the resistor network once again. We have this voltage source, we have this resistor on top, then we have this resistor adjacent to the voltage source, and then we have this another 35 ohm resistor, and then the last resistor that we have would be REQ4. Take note that these are all 35, 35, and 35. What we can obviously do next is to add this resistor network, and we call that as our REQ5. So REQ5 is simply equal to 35 plus REQ4, which is 30, and as simple as that, REQ5 is equal to 65 ohms. So yeah, that's it, 65 ohms. And to further simplify the resistor network, we can add REQ5 with its parallel resistor, which is another 35 resistor ohm, and we call that as our REQ6. So REQ6 is simply a parallel sum of these resistors right here. So we have to write again 35 times REQ5, which is 65 ohms, divided by its sum, 35 plus 65. So we have 35 times 65, that's equal to 2,275 times divided by 35 plus 65, so that's 100. And REQ6 then is equal to 2275 divided by 100, that's 22.75. So yeah, that's our REQ6. Just gonna write it right there. So we have our REQ6 as 22.75 rather, not 65. There, 22.75. And the last resistor network that we can obtain from this diagram is to add this finally to this last remaining resistor, and they are all in series, and we're going to call it REQ7. So that's the final resistance that we can calculate from this diagram. So REQ7 is simply equal to the series resistor, sum of series resistors. So the final 35 ohm plus REQ6, which is valued at 22.75 ohms. So we're just going to add that with 35, and we have REQ7 is equal to 57.75 ohms. So in short, REQ7 is the total value of the resistor network. This is also the value of resistance that our voltage source here is seeing. So since we have the voltage source, which is 20 volts, and we have the equivalent overall resistance of 57.75 ohms, we can now solve for you can now solve for I by Ohm's law. So Ohm's law is a very straightforward approach to calculating the missing element, which is in this instance the current I. So current I is equal to voltage V over resistance R, and our voltage is 20 volts divided by 57.75 ohms. So 20 divided by 57.75, that would be equal to, our current would be equal to 0.346 amperes. So that's a very small amount of current, and that's our final answer. So it is important that when you solve a problem, you need to box the final answer and perhaps label, and don't forget to place a unit of measure in your problem set. So yep, going back to this diagram, we have now solved the value of I, which is equal to 0.346 amperes. Notice that our current is very small, and in instances such as this one, limit your answers to 3 decimal places only. Though in reality, you need to be more precise than that, because very small amount of current is not something that is unusual. In fact, it is very usual, especially in electronics. So you need to have a precise measurement of the current. But more onto that, the next task that we have here is to solve for VO, which is unfortunately located at the last branch, or the farthest branch from our voltage source. So yeah, solving for VO. In order to solve for VO, we need to re-expand the network once again. So we are gonna start with the second to the last version of the simplified circuit diagram. So in this case, this is the network that we are gonna start with, and from what I recall, this is what we know as equivalent resistor 6 or REQ 6. So to redraw the diagram, we have, so we know that as 35, and we have here is our simplified resistor diagram, and we know this as our REQ5. Notice that I've talked about REQ6 earlier, but if we are gonna expand the resistor network equivalent to REQ6, that will be equal to the parallel equivalent of 35 ohms and the resistor network REQ5. So just to draw the current here, that's the current I that we just solved not very long time ago. So what we can do next is we can do a current division formula in this re-expanded circuit resistor network. So by current division, in order to solve for the current here, we have just to label it as our current for REQ5, so that's very small. In order to solve for the current at REQ5, we have to look at its opposite resistor, which is in this case 35 ohms divided by the value of 35 ohms plus REQ5. Recalling the value of REQ5 is 65 ohms, so we're just gonna put 65 ohms right here. All of that is multiplied with the value of our main current, which is 0.346 amperes. So we can then solve for our current at REQ5. So we have 35 plus 65 is equal to 100. So we have 35 divided by 100 times 0.346. That's equal to 0.121 amperes. So that's relatively a very small amount of current that flows in our REQ5. So re-expanding the network once again, we have to determine the equivalent resistor network for REQ5. We have REQ5 is simply the series connection between 35 here, 35 and REQ4. So we have learned that in series circuits, the current is the same throughout. So we don't need to do a current division for that. So we will go straight to REQ4 instead and look for its equivalent resistor network. So we have known from this previous solution that Req4 is equal to the parallel sum of Req2 and Req3. So we're gonna go back here and trying my best to redraw the diagram. So we have a parallel resistor here between Req3 and Req2. So drawing once again another parallel resistor, and this time the current here, the main current that enters through this branch would be our current at Req5. So we have known the value of Req5 as 0.121 amperes, and we are yet to do another current division formula. So let's say that the current here is the current Req2. So, and obviously the current here is Req3. But our concern here is to solve for the current at this branch, Req2. So, we'll go straight to that. No. The current at Req2 is equal to the opposing resistance, which is Req3, divided by the sum of the resistance Req2 plus Req3 times the value of this main current here, which is I, or the current in Req5. Replacing this with values of Req3 and Req2, recalling from this solution right here we have Req2, and right here we have Req3. So Req3 then is equal to 52.5. So we're just gonna write 52.5 divided by 70 plus 52.5 times 0.121. So 52.5 plus 70, that's 122.5. 52.5 divided by 122.5 times 0.121, and our current at Req2 is very small at 0.052 ampere. So this is just rounded up to 3 decimal places. And we have the current for Req, for the current for Req2. So recalling from this original diagram, this is Req2. Just gonna write it there. We have Req2, and once again recalling that for series circuits, our current is equal all throughout. So basically what I'm saying to you is that we have already found that the current that flows here is current I subscript Req2. So that's the final value of current that we want to find in this diagram in order to solve for VO. So recalling from Ohm's law, wherein current is equal to voltage divided by resistance, doing a small tweak at the formula, we have voltage VO is equal to current I Req2 times the resistance, which is 35 ohms. So this is a lengthy solution. By Ohm's law, we have VO is equal to I R EQ2 times 35, and we have known that the current at REQ2 is 0.052 amperes, so we're just going to multiply that with 35 ohms, and we can now solve the value for VO. 0.052 times 35, and that is equal to 1.82 volts. So that's our final answer right there. We don't need to tweak that for its sign convention, because the indicated sign convention for VO is similar to the voltage source, so we don't need to reciprocate the sign convention for our VO, and this is our final answer. This is the voltage at the last 35 ohm resistor. So that is how you are gonna solve for VO. And what makes it particularly tricky is that your solution will be very lengthy, and you need to be prompt in doing your solutions, because if you missed a single step on this, the succeeding calculations uh, would be wrong. So that is how you are gonna approach this particular problem. I'm sorry that my handwriting and my diagram are not the best, but hopefully you can take your time to draw and redraw the diagram, and perhaps do a more clean solution, in fact cleaner than this one. So yep, all the best in your assessment. Thank you so much.